Welcome to the dawn of the 6G era. By 2030, we expect over 29 billion devices to be connected at all times. Leading cellular network providers predict a massive influx of data that current infrastructures simply cannot handle. This isn't just about more smartphones. It's about a world where every machine, vehicle, and sensor is part of a unified digital fabric. Future smart cities will be defined by ultra-reliable low-latency communications and massive IoT connectivity. We are targeting peak data rates of 1 terabit per second. That is 1,000 billion bits moving every second. Latency will drop to less than 0.1 milliseconds, enabling life-safety applications like remote surgery and autonomous flight. This density requires a total rethink of our spectrum. We are building the foundation for a truly holographic society. This is the 6G vision, a world connected at the speed of thought. Our journey begins here, at the boundary of the invisible. We are settling a new land where data flows without limits. We will uncover the physics and engineering that make it possible. This is not just an evolution. It is a revolution in how we connect. Every megahertz we unlock brings us closer to the terabit era. 6G technology aims to support massive connectivity and extreme data rates through the terahertz band. Welcome to the next frontier of wireless technology, a planet unified by light and data. Imagine a world where data moves at the speed of thought, a world of infinite possibility. We are building the engines of the next decade, tiny circuits for giant data flows. Welcome to the era of terahertz. Let's look at the very fabric of the spectrum and the unique challenges it presents. The terahertz band, spanning from 0.1 to 10 terahertz, is the final piece of the radio frequency puzzle. It sits between the world of radio and the world of light, combining the best of both. Here, wave physics changes dramatically. At these high frequencies, the wavelength is sub-millimeter, allowing for massive integration of antenna elements. We gain tens of gigahertz of contiguous bandwidth, allowing for picosecond-level symbol durations and extreme data density. But mastering this space requires us to overcome the terahertz gap, the historical lack of efficient transceivers. Now, breakthroughs in materials, science, and nanotechnology are making it possible to settle this invisible frontier. The terahertz band is the foundation upon which the next decade of wireless innovation will be built. It is the invisible backbone of the 6G revolution, enabling a truly holographic and sentient society. As we climb higher into the spectrum, we must adapt our technology to meet the fierce requirements of physics. Every megahertz we unlock brings us closer to the terabit era, where information moves at the speed of light. This spectral landscape offers integration of thousands of sub-millimeter-long antennas on a single transceiver chip. Ease of coexistence with other regulated spectrum makes it a perfect candidate for resolving spectrum scarcity. It is the key enabler for larger data rates, higher quality of service, and lower delay in the next generation. We are mapping a new spectral landscape where bandwidth is no longer a constraint but an abundant resource. Welcome to the era of terahertz. Let's explore the physics of propagation and the hurdle of molecular absorption. Terahertz waves behave differently than the radio waves we use today. They have stronger corpuscular properties, behaving more like particles of light. This means path loss is significant, and signal propagation is dominated by line-of-sight requirements. We must model these channels with extreme precision, accounting for frequency selectivity. Unlike lower frequencies, terahertz signals do not diffract around obstacles. They create sharp shadows, creating coverage holes we must solve. We analyze propagation in both indoor and outdoor environments. Propagation has two aspects: path loss and molecular absorption. These factors fundamentally constrain system design. We extract channel parameters to build mathematical representations. Attention includes delay, angle, Doppler frequency, and polarization. Models must represent the physical environment in detail. We are turning the physics of the environment into a design parameter. Accuracy is the key to reliability in a world of straight lines. Every reflection and blockage must be accounted for in 6G. Molecular absorption is our greatest hurdle. Air molecules like oxygen and water vapor consume the signal's energy. This leads to extreme frequency selectivity, filtering the atmosphere. Absorption peaks at 380 and 448 GHz make the air opaque. However, between these peaks lie transmittance windows. Selecting these frequencies enables reliable long-distance links. This requires adaptive spectrum management based on real-time humidity. We are turning the atmosphere from a barrier into a medium of study. It is precision engineering where we select the perfect window. Humidity is no longer just weather, it's a network variable. We engineer signals to weave through the molecules of the air. Attenuation and interference can be calculated at the transmitter. Allocated frequencies are selected based on targeted user needs. We master the atmosphere to unlock the full potential of 6G. This is the key to mastering the invisible medium of data. To build the hardware, we are pursuing multiple pathways. The electronic approach pushes silicon CMOS and silicon germanium to their absolute limits. We are fabricating high-mobility transistors using semiconductors like indium phosphide. We use frequency-multiplying chains, doublers and triplers, to upconvert signals. These electronic systems face challenges with waveform distortion and phase noise. But with sophisticated digital backends, we are overcoming these bottlenecks. We are building the engines of the terabit era on a single chip. These are tiny circuits designed for giant data flows. We are integrating thousands of antennas onto a single transceiver. Every micron of silicon is optimized for terahertz performance. The goal is to push existing technologies for microwave and wave devices. Resonant tunneling diodes and impact diodes are key examples. Sub-milliwatt emissions are expected, while watts have been demonstrated with tubes. The digital bottleneck posed by converters is another major hurdle. State-of-the-art converters sampling at frequencies in excess of 100 gigasamples per second. The second pathway is photonics. By leveraging light, we generate terahertz signals with incredible spectral purity. Quantum cascade lasers and frequency difference generation are leading the way. These systems use optical techniques to create reachable 6G frequencies. Photonics offers much higher bandwidths than electronic systems. Quantum cascade lasers emit low-energy photons corresponding to terahertz. Carrier signals are generated by photomixing two optical carrier signals. We are moving toward room temperature operation for these laser systems. Hybrid systems are the key to future backhaul and space links. We are blending the world of fiber optics with the world of wireless. This is the era of light-based communication. We are using lasers to carry the world's data. Precision, purity, and power define this approach. Photonics is the bridge to the stars. We are building a network that moves at the speed of light. Perhaps the most revolutionary pathway is plasmonics. By using graphene, we can create devices that operate at terahertz frequencies intrinsically. Graphene's high electron mobility allows for the propagation of surface plasmon polariton waves. These plasmonic nano-antennas are incredibly small, 2 orders of magnitude smaller than metallic antennas. This allows them to be integrated directly into chips for wireless networks on chip. This is the future of integrated nanoelectronics. We are using the unique properties of two-dimensional materials to bridge the terahertz gap. Plasmonic modulators can reach speeds that electronic modulators can only dream of. We are building a world of light and matter in perfect harmony, communicating at the atomic scale. Graphene is the key to the next generation of sensors. It is a material that defines 6G. We are harnessing the global oscillation of electrical charges. This is the plasmonic revolution. This approach offers high reward, arising from true terahertz operation and ultra-broadband bandwidths. We are leveraging the fundamental properties of new nanomaterials to solve old problems. The plasmonic pathway is our ticket to the nanoscale connectivity of the future. This is the ultimate union of materials, science, and communication engineering. Tiny antennas, massive impact. Because terahertz waves have tiny sub-millimeter wavelengths, we pack thousands of antennas into one device. This enables ultramassive MIMO, using hybrid beamforming to focus signals into razor-sharp beams. These beams track users with millidegree precision, compensating for the high path loss of the band. However, we must solve beam squint, where frequencies travel in slightly different directions. Using true time delay circuits, we ensure our beams stay perfectly aligned even at terabit speeds. This is precision at the scale of light. One beam, zero waste. We are using spatial multiplexing to send multiple data streams over the same frequency. Every antenna element is a design parameter. We are building arrays with over 1,000 elements. This is the ultimate tool for combating distance limitations, focusing energy exactly where it's needed. This is the power of ultramassive MIMO. We are effectively turning antennas into digital lenses. These massive arrays will be integrated with dielectric lenses to further increase gain and dynamic capabilities. Silicon lenses printed on top of on-chip antennas can provide up to 30 dBi of gain. We are engineering the wavefront itself, using self-healing Bessel beams and bending Airy beams. This is the next level of antenna engineering, where we control the signal with surgical precision, focus, direction, and density. Beam management is the heartbeat of the 6G network. Focus is our strength. Since terahertz waves are easily blocked by walls or people, we must engineer the environment itself. Reconfigurable intelligent surfaces, or RIS, are the answer. These are smart skins applied to buildings. By acting as digital mirrors, they can bypass obstacles and extend coverage into shadow zones. These surfaces are programmable, allowing the network to dynamically optimize the propagation path. In 6G, the world around you becomes an active part of the communication network. Every wall, window, and surface ensures your connection never breaks. We are building a smart radio environment where signal propagation is a design parameter. The city becomes the network. Every surface is a digital mirror. We are bypassing blockages with programmable reflections. This is the future of urban connectivity. The environment is alive with data. We are engineering the world to be connected. Metasurfaces can regulate electromagnetic reflections by creating a controlled discontinuity. They received great attention as they can increase coverage considerably in the terahertz band. The high frequencies will enable the deployment of a large number of metasurfaces in a small area. We are turning the static physical world into a dynamic, programmable radio environment. Coverage is no longer a luxury. It is a fundamental property of our smart surroundings. This is the RIS revolution. At the networking layer, narrow beams create a deafness problem. Devices must be perfectly aligned. We are developing receiver-initiated MAC protocols, where users sweep the space to discover neighbors. To speed up discovery, we can use the terahertz rainbow, illuminating space with different frequencies. We are also exploring dual radio systems, where microwave signals handle control and synchronization. This ensures ultra-fast link setup and rock-solid reliability for 6G networks. Synchronization is the heartbeat of data. Every pulse must be timed with picosecond precision. We are building the protocols for the terabit era. Timing is everything. We are coordinating billions of devices with absolute precision. This is the MAC layer of the future. We are solving the deafness problem with frequency-based discovery, rock-solid and incredibly fast. 6G is a network of perfect timing. Synchronization is the key to efficiency. The need for high-gain directional antennas makes link layer synchronization extremely challenging. Neighbor discovery is a resource-consuming process when narrow beams are used without a control channel. Our solution uses receiver-initiated handshakes and aggregated packet flow control. We are also exploring non-orthogonal multiple access, or NOMA, to improve spectral efficiency. This is the brain of the 6G network, managing billions of connections with flawless timing. In dense 6G deployments, managing interference is critical. High-gain beams require careful management. While terahertz's short range naturally limits interference, misdirected signals can be devastating. We are modeling coverage using 3D ray tracing to account for every reflection and blockage. To provide 93% coverage, we recommend an access point density of 1 every 7 meters. We are also developing distance-aware resource allocation, maximizing spectral efficiency. Every device gets exactly the bandwidth it needs, exactly when it needs it. Seamless coverage everywhere. We are optimizing every square meter of the 6G world. Interference is managed with surgical precision. We are building the densest network in human history. Coverage is a guarantee, not a luxury. We are maximizing the spectrum for everyone. Density is the new standard. Coverage without limits. Denser nodes and longer transmission distances result in lower coverage probability. Recent research focuses on using reinforcement learning for interference detection and mitigation. Multiple access points can remarkably increase the coverage probability in dense office layouts. We are proposing the nearest line-of-sight access point association to outperform traditional methods. This is how we provide high-quality service in the densest 6G environments. Every point is an opportunity. We are building a world without signal dead zones. Density, coverage, and efficiency. This is the 6G promise. Terahertz links are inherently short-range, so 6G will rely on multi-hop communication. Data will leap from device to device, using both active and passive relays to extend reach. This requires incredibly fast routing and scheduling. Device buffers can fill up in microseconds. We are applying machine learning and artificial intelligence to manage these high-speed data flows. AI predicts user movement and network congestion before they happen, finding the optimal path. AI-driven routing balances latency, power consumption, and reliability for a seamless experience. Intelligence moves the data, the network thinks. We are building a mesh that adapts in real time. Every device is a relay. Every hop is optimized by AI. This is the neural network of 6G. We are routing data at the speed of thought. Congestion is predicted and avoided. The network is self-healing. 6G is more than just speed. It's smart. Intelligence is integrated into every packet. Optimal connection paths might change frequently due to high directivity and fast-varying channels. We are employing tabular reinforcement learning for routing protocol design, considering limited buffers. This ensures timely optimal throughput even in bufferless environments. 6G is a self-optimizing organism. Routing at the speed of light, intelligence in every hop, the future is an AI-managed fabric. We are settling a new land where data flows without limits. Intelligence moves the world.